Okay, so let's, actually I just have 4 here that are different from each other. So we have boron. This is the complete lecture 74. So here is boron, Bf4 minus. Now this is a polyatomic ion, so we have to put it in square brackets. Boron is 2s, 2p, 1, 2, 3. Now we need 4 half-filled orbitals. By promoting one of the electrons here, we get 3, but we need a 4th, and that's where this charge comes in. That -1 is the extra electron. If it was -2, we'd have 2 electrons to work with. If it's positive, then we have to get rid of one of the electrons. But here, that's the 4. Then we get sp3 for each of these. And do it very quickly here. This is tetrahedral. The fluorine comes in, completes the bond. Oops. And these are 2p's, 2p, 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 sp3, 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 sp3. And the big thing here is once you draw the structure, you have to put a big square brackets around it and a minus to indicate the charge. So don't forget that. Then we have ClF4, 35 electrons for those 5 halogens, but we lose one because of the charge, so 34. So it has 4 bonds, and then a lone pair to it. And this has, again, it's a charge, so we have to put the square brackets around it. And then we have the chlorine. Now, there's 1 of 2 ways to do this. We know we need 5 orbitals, so, and we have them with the 3D here. So we could just draw out chlorine, the orbital diagram of chlorine. And then then we promote 1 electron, so we have 3 bonding. No, that's not enough. Now we have 5 bonding orbitals and 1 lone pair. So we have 5 bonding orbitals, but notice we have that plus sign there. It means we've lost 1 electron, so get rid of that one, and we're all set. We have all 5. Or you could have just taken away the electron before you got started and thought of this as chlorine plus. And you could do that too. Just make sure that you show why it is that you seem to be missing one of your electrons. As long as you show that on the exam, that's fine. And then we have chlorine, Trigonal bipyramidal. Drawing is getting worse, but I've been doing this for 2 straight hours. So just to keep. Oh, now this is a lone pair here. So 2p, 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 and then these are all sp3d. This one, this one, this one, this one, and this one. And you know, it's getting messy, but yeah. So on the exam, you won't be writing, well, more than 20 in a row. Whole bunches of these guys. For me, you guys will only have a few to do. So make sure that they're nice and neat as much as you can do. Now let's go on to atoms that, or molecules that have 2 central atoms. We've done this in the past with the Lewis structures. That's what we end up with. We know that we have a double bond there. Now we haven't talked about this before, but any single bond is considered what is called a sigma bond. Unfortunately, they sound very similar. Single bonds are sigma bonds, and that sigma means that the bond is directed between the atoms. But a double bond has 1 sigma and a pi bond. Now what that means is that when the carbons come together, they form what we normally think of as a bond, where the orbitals go between the atoms, but then they also each have a p orbital that remains unhybridized that bonds above and below. Even though this is a p orbital, it has 2 lobes, it's just one bond, or it's 1 orbital, so it forms a bond above and below, but that's still considered just 1 bond. So here's our sigma bond, here's our pi bond. So we need to have, now we have to alter our rules a little bit. For every sigma bond to an atom, we need a half-filled orbital. that we hybridize. For every pi bond, we need one half-filled p orbital that we leave unhybridized. So look at the carbon. If it's true for one carbon, it's true for the other. So you only need to deal with one carbon here. If these were two different atoms, we'd have to do it for both, but this is 2s, 2p. So we need 4 bonds still. So we need 4 half-filled orbitals, but we need one that's one p orbital that's left alone. So if we promote the electrons, now we have everything we need. We have 3 orbitals that will be involved in the hybridization. So these become sp2s. And then we have one 2p orbital that's left alone. That's just brought right down, but it's still involved in bonding. So this is new. So we have an sp2, an sp2, and an sp2. We have the hydrogens that attach here with their 1s. Now the new thing is that this sp2, instead of going to a hydrogen, goes to the other carbon, and they overlap their sp2 orbitals. And this is how carbon bonds to itself, and it can do it over and over again, and it's really the basis. This type of bonding is the basis for all of organic chemistry. Carbon likes to bond to itself. So these are all sigma bonds. So you might be asked to label the sigma bonds. All of the single bonds before were sigma as well, but we just didn't know there was anything else. And then we have a 2p orbital. I'm going to kind of exaggerate it. There's a 2p orbital here and a 2p orbital here, and if they overlap, they form a pi bond. Now, for acetylene, we have a triple bond. So these are sigma bonds. The single bonds are sigma. When you have a triple bond, though, you have a sigma, and then you have 2 pi bonds, which means you have 2 unhybridized p orbitals off of each carbon overlapping. Now you see this this p orbital. So this all is in the plane of these p orbitals here are in the plane of the paper, but we could also fit in another p orbital here on each one, creating kind of a barrel of electron density around. So there's plenty of room for a triple bond. So if you ever wondered why you have 6 electrons, how they can all fit between the atoms, especially 2 small atoms like this, they don't. There's only 2 that go between the atoms, and then there's 2 above and below, and then 2 to the left and to the right. So there's plenty of room for that. So what we need is carbon now. We have 2s and 2p, like that. We promote an electron. Now we only hybridize these, so these are sp orbitals. And then we leave 2 of the p orbitals alone. So that's new, but that's how we do this. Carbon then, the sps we know create linear molecules. Or we should. We know that each of the hybridized orbitals create a different geometry. The sps are linear. So we have 1s, 1s. These are sp, 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 and sp. And then the 2p we have. I'm going to really exaggerate it so that they look different from each other. They're not this skinny, but that'd be your 1p orbital, or pi bond from the 2p orbitals, so we can call this 2p and 2p. And remember, even though it has 2 lobes, it's just 1 orbital. And then we have the other one. We draw the best we can do for a three-dimensional look is to do an angular thing, but you picture that these 4 atoms and the 2p orbitals are in the plane of the paper, and then these are jutting out, and this would be a pi orbital. Now I know that's difficult to draw for some people, so just do your best. I should be able to see what you're doing. So then you label everything in that way, and you're all set.